Today I'm going to talk about an optimal Liouville type theorem for the porous medium equation. This is a joint work with Rafayel from UFPB. And I tried to organize the talk as simple as possible, not to complicate with the proofs and stuff. So I'm going to just talk about what we mean by Liouville type theorem, what is known, and what do we mean when saying optimal Liouville type theorem, and some sketch of the proof. So as we all know, the classical Liouville theorem for the harmonic functions states something like this: like if you have bounded harmonic function in the whole space, then it must be constant. No, it's zero. Well, of course, it's in one point, it's zero. Bounded harmonic functions in the whole space are constant. So the same conclusion is valid for parabolic equations as well, apparently. So you have parabolic, the caloric function in the space, and it's bounded, then it has to be a constant. By the way, these solutions that are in R minus, so in past time, in literature, they are kind of referred to as ancient solutions. So ancient solutions must be constant. But there is a key difference between parabolic and elliptic equations, because, for example, in elliptic equations, one-sided bound is enough for the conclusion to hold. Namely, like if you have, let's say, non-negative harmonic, entire harmonic function, then it has to be a constant. But this claim is not true for parabolic equations. Like one-sided bound is not enough, as shows this classical example, which this function u is obviously non-negative, solves the heat equation in the whole space, and obviously is not a constant. But as theory evolved, then Bernstein noticed that the growth condition, the boundedness can be compensated by a growth condition. So you can, and he noted something like this, that the entire solutions of uniformly elliptic equations, say Laplacian, growing sublinearly at infinity must be constant. And what is interesting about this claim is that it holds also for parabolic equations. So one-sided bound was not enough for parabolic equations, for the Liouville type theorem to hold. But Bernstein type argument, so if you have some sort of control of the growth, your solutions must be constant. There is also a key difference whether you are looking to a homogeneous equation or inhomogeneous equation. So far, we were talking about homogeneous equations, that is right-hand side is zero. But if you are looking for inhomogeneous equations, so the right-hand side is something different than zero, then even one-sided bound, even for uniformly elliptic equations, is not enough, as shows the example of this function x squared, which solves this equation, so solves Laplacian for this inhomogeneous right-hand side, and is non-negative, obviously, and obviously is not a constant. So there is no Liouville type theorem once you allow right-hand side to be different than zero. The recent developments in regularity theory boosted some class of Liouville type theorems for large class of operators. And one of them, for example, being for p-caloric functions, this was shown by Teixeira and Urbano. They say that, okay, if you have an entire solution of this entire p-caloric function, and then you suitably, in some intrinsic manner, control the growth of this function at infinity, then the function must be constant, right? And as there are local regularity results for porous medium type equations, similar result holds also for the porous medium equation. This one, I guess I recently saw, is shown in a paper, if I remember correctly, the authors, Jovito, Gleitson, Picarci, and Gianni, and one student. Correct me if I'm wrong. So Liouville type theorem, also proved by Teixeira and Urbano, holds also for porous medium equation. However, so this is what we mean by some intrinsic manner. So you have C alpha regularity in time and alpha over 2 in C alpha in space and alpha over 2 in time. And you have control at infinity, something like this, then your solutions must be constant. However, as you may notice, this alpha, since porous medium equation has solutions that have faster growth rate, one may expect that there is some sort of upper bound for this alpha. And we tried to find this optimal alpha, like how far we can go, how weak we can make our condition. So this is an example of a solution that grows faster. And that is what we tried to address here. And before stating the results, I'm gonna just give some definitions. This is the intrinsic cylinder, the lower cylinder. So BRX is the ball centered at X with a radius R. And this is the lower cylinder. And when X and T are 0, we simply just write GR, meaning X and T are 0. So G1, for example, would be B1, 0 multiplied by -1, 0, right? And this is the intrinsic norm. We are going to use this notation to describe what kind of growth we assume at infinity. And this gamma, let me remind that this gamma from the porous medium equation, right? And we are going to look for solutions in these T-level strips, as we call. So you go up to T. The T is any number in R, and you cut this strip. So we are going to look equations in this strip. And when we are talking about entire solutions, we are going to talk about solutions. We mean solutions in the strip. So it can be anything in space and up to the time T. And the results are based on the recent regularity result by Damian, which says like if you are close to the heat equation, so if your gamma is small enough, your equation becomes quite close to the heat equation, then non-negative solutions, and we are always going to assume the right-hand side is at infinity. Then across this boundary of the positivity set, you have this growth control for the solutions. And where this intrinsic norm is defined as above. And this exponent 2 over gamma plus 1 is optimal. So not only it's sharp, but it's optimal growth condition. And we are going to assume that we are always in this regularity regime. So the gamma will be small enough, so we are close to the heat equation, and we have this regularity regime. And what we state is this. So if you have non-negative solution of the porous medium equation in a strip, I remind you that we defined the strip as so anything in space and the time up to time T. So if you are looking at the non-negative solutions of porous medium equation in a strip, which vanishes at a point, and at infinity, growth is controlled in this intrinsic manner, then it must be 0 up to that point where it vanishes. So if it vanishes at one point, it must vanish all the time up to that point. So I call this G to refer later. So this is the growth condition, intrinsic growth condition. Then once I'm going to sketch the proof of this theorem, but there is something interesting happening. Like if you are looking at the equation, the homogeneous equation, so when you assume f equal to 0, something even better happens. Then you don't need to look growth at infinity in time. You just have to look growth in space. I'm going to state it below. Let me just comment that this condition G cannot be weakened, meaning that this exponent 2 over sigma gamma plus 1 is the best we can get. Like the condition cannot be any weaker than that. That if this exponent is just a bit bigger, the conclusion fails. And it shows the following example. So if you look at this function, modulo of x to the power 2 over gamma plus 1, it solves the porous medium equation with some L infinity right-hand side. It vanishes at the points 0 times r, right? Wherever x is 0, this vanishes. And satisfies to this condition G for any exponent sigma, which is just a tiny bit bigger than what we have here. But the function obviously is not identically 0. So this condition G, this exponent here, 2 over gamma plus 1, cannot be weaker. So in that sense, that's optimal. That's what we mean. Okay, so now if you look at the homogeneous equation, this condition G can be substituted by this. So you look at the growth only in the space variable. The time doesn't matter anymore. And the conclusion still holds. So if U is non-negative solution of the porous medium equation in the strip and vanishes at one point and has a growth that is controlled in space direction in faraway points, then the solution must be 0 up to that time where it is vanishing. And this, I'm going to refer to it as S, meaning that growth in space variable only. So how do we prove? Actually, this second theorem seems a bit stronger, but in fact, it is a consequence of the first one. And I'm going to say a word or two on proof of that too. So how do we prove the first one, for example? This exponent, let's just denote it sigma, not to repeat all the time. And we just rescale it. We define these UK functions, which solves the porous medium equation with some bounded right-hand side. We assume that the original right-hand side was L infinity. And obviously it's all of them, all these UK functions vanish at 0. Because when you look at the point 0, 0, you get the value U x0 t0 over k sigma. And U x0 t0 was assumed to be 0. So all of them vanish at 0. And we check that L infinity norms of this function go to 0 in some lower cylinder. And I didn't write down the proof of this just not to complicate the slides, but the idea is very simple. Like you assume it's not true and you immediately come to the contradiction with the definition of the UK. So once one is shown, then you just simply, for any point in the strip, I remind that this is up to the time t0, so t0 included as we are looking at the closure. If you take any point of this, so the first equality here is simply the definition of UK, right? And then since you can choose k big enough, you can make sure that this point where UK is applied is in a regime where this norm of UK goes to 0, right? And then this less than or equal to, this is the regularity estimate proved by Araújo recently. As we assumed, we are in the regularity regime. And so gamma was very small, so we are in this regularity regime. So simply we are applying this regularity result for the UK to estimate the UK norm. and that's what was written here. So the second, this inequality here is the regularity result. And yeah, now is just recalling the definition of this norm, the intrinsic norm, k sigma times all this is simply equal to this, just recalling the definition. Now, if you look at 1, so the norm of UK goes to 0 as k goes to infinity, which means that this u y tau, which was non-negative, can be made as small as we wish. So it has to be 0, right? So basically, this was the whole proof. So I omitted this part, the proof of this, which is a contradictory assumption. So and we conclude the proof. So what we get this, if you have a non-negative solution of porous medium equation, which is near the heat equation, so gamma is pretty small, in a strip, which vanishes at a point and has this intrinsic growth at infinity, then it must vanish up to that time at all points. And now how do we infer this second claim from the first one? So once your right-hand side is 0, we say that we claim that no need to look at this intrinsic scaling depending on time already. There is no time involved anymore. So it's enough to look at the growth only in the space variable. So how do we do? Actually, we make sure that once you have this growth condition in space, once you have S, then you have also this G condition, which seems a bit counterintuitive, but here is how to make sure of that. Okay, so this is what I'm saying. We have S, we have growth only in space variable, and we are gonna make sure that G is true. And we do again by a contradictory assumption. We say, let's assume that's not the case. That's not the case. It means there is a subsequence and some strictly positive number that as your intrinsic, that one fails, so which means second holds. That is, the farther you go, doesn't matter how far you go, you will still have this ratio strictly over 0. But what it means, this norm going to infinity, you have two cases. Let me remind what it means, the definition. The definition of the intrinsic norm is here. So once, what it means, this norm going to infinity. So either this one goes to infinity or this one, or both of them, right? So let's make cases with the first one. So either module of X goes to infinity or it's bounded. And okay, let's here. Okay, once this goes to infinity, then either module of xi goes to infinity, or if it's bounded, then ti goes to minus infinity, because we are in the strip. There is no positive time. We are only looking at the ancient solutions, right? But if we are in the first case, so once your xi goes to infinity, then S, which is this, I'm sorry. So once your X goes to infinity, you know that your solution U has this, behaves like this. So it's all small like that. So if you are in the first case, which was xy going to infinity, you know that U behaves like this. So you put together with this, you get a contradiction, right? Because on one side, you get it's going to 0. On the other side, it has to be strictly above the 0. So it's not the first case. Xi cannot go to infinity, so we have to be in the second case. Xi is bounded for some r, and we are going to infinity using the time variable. Otherwise, this will not go to infinity. So, but in the second case, if you choose some tau like this, smaller than this ugly number, this px1 t1 is the paraboloid defined like this. So once you choose tau smaller than t1 minus this number, you can ensure that any point if br times tau is in this paraboloid. And why is that important? Because there is this result by Di Benedetto, Giuseppe, and Vespri, which says once you are in the paraboloid and your infimum is 0, and in our case is 0 because U vanishes at a point, then as t goes to infinity, your solution vanishes. And moreover, this convergence has to be uniform in BR. BR was this pair here. So as you choose tau so small, and you can always choose because your ti is as small as you wish, you are looking on that time, ancient times. So it has to be uniform. But this means, so you look the first one in particular, this means that you can make it less than, for example, C star over 2. And you put it together with this condition. So in one side, it has to be smaller than C star over 2. On the other side, it's bigger. So this is another contradiction. And what contradiction shows that this condition G holds, right? We assumed it fails and we got a contradiction. But once G holds, we know that U vanishes up to the time t0. So the second case is also remains true. And yeah, basically this was what I wanted to show. There is an expectation that you should be able to go even a bit more than t0. So your Liouville time theorem, your solution must vanish not only up to the time t0, but perhaps also a bit more. But this induces some changes in scaling, and the regularity result needs to be adjusted. And I'm not sure it's an easy task. So that's why we stopped here once we were able to finish like that. So condition, this contradicts as I already told, and I finish here. Thank you for the attention.